So in the previous video, we talked rather generally of how we revolve functions around axes to trace out shapes in which we're wondering what their volumes are. So some of the things we talked about before were kind of tracing out this cone-like shape when we revolve that line around the x-axis, or how we revolve this kind of more curvy function around the x-axis, and then found a little more complicated shape that we probably don't know its volume right off the bat. So for us in class, we're going to go through the derivation of this formula, but what will help us out in a little bit is knowing that the general idea for volume of an object when revolved around a particular axis will be the integral of some starting place to some ending place of pi times what we call the radius, that in this case we'll say is a function of x. And the radius is going to be squared. And hopefully this formula feels very familiar, like the pi times radius squared is the area of a circle. So for us, the way we think about this radius is the distance between the function we're revolving and the axis we're revolving it about. So let's go through a very basic kind of example in this case. So say we have the following parabola. We just have a regular old parabola, say y equals x squared. And we're interested in figuring out the volume when revolved around the x-axis between, say, 0 and 1. So x equals 0 would be there, and we could say x equals 1 is somewhere, over on the right-hand side. So if we revolve this function, it's going to trace out a almost like hyperbolic looking cone, if you will. So I'll just draw kind of what it looks like down here. That's a really poor drawing, but it's tracing out some curvy-like cone-like thing. So for us, what we need to do for this problem is go back to our formula for how we compute volumes. So for us, I like doing this in a very step-by-step process. The first step I do is determine the axes we're revolving around. In this case, our problem said, hey, let's revolve around the x-axis. And the reason I want to start off the bat with that is because the next step for us is to determine the radius. And this is really the radius between the axes and the function we're revolving around. So for us in this case, if we zoom into our function, our radius is defined as the distance between our function and the axes we're revolving around, which is that x-axis. So in this particular example, our radius function is going to be equal to the distance between those two things, the function and axes of revolution. So for us in this case, our function is x squared, and our axis is at x equal or y equals 0. So that would be the distance between those two things. So just to make this a little more clear, this x squared is the top function for us. And y equals 0, so I'll just be clear, this is y equals x squared is the top function, and y equals 0 is the bottom function. That's basically the function that's telling us where the axis is. So our radius in this case is just, well, it's x squared. The third thing in this problem, determine the bounds of integration. And in this particular problem, I basically just told us the bounds we're going to use. We're going to go from x equals 0 to x equals 1. Now, the reason why this is step 3 is sometimes you might have to think about the intersection points of functions to figure out what the bounds are going to be for the integration kind of aspects. But for us starting off the bat, these are the bounds we're going to use in this example. We'll go through those other cases together. The fourth step is putting it all together. So again, if we revisit our volume formula from up above, we had that the volume is equal to x equals a to x equals b, the top and bottom bounds, pi times our radius function squared. So our bottom bound is x equals 0. Our top bound is x equals 1. We have pi, and then times our radius function, which in this case we saw was x squared minus 0. Now, of course, that minus 0 really won't matter for us. I guess let's remember to square it before we forget. Dx. I just like putting this 0 here to really remind us we're computing the distance between two things. And this might be a little bit of a spoiler in saying once we start revolving around, say, different axes. So what if we revolved around the line y equals minus 3? That 0 is going to turn into something different. But in general, we have our formula for the volume of this kind of function between 0 and 1 when we revolve it around the x-axis. So if we just go ahead and compute this integral now, this is the integral of 0 to 1 of pi times, well, x squared would be x to the 4th dx. And that pi, of course, is a constant. When we now just have a variable raised to a constant, we get to use the antiderivative power rule. So that'd be pi times 1/5 x to the 5th, and we get to evaluate that at x equals 0 and x equals 1. So if we just plug in those bounds again, we plug in the top bound, or the antiderivative evaluate at the top bound, minus the bottom bound. We have 1/5 times 1 to the 5th power minus 1/5 times 0 raised to the 5th power. And of course, the second term, since we're evaluating at 0 to some power, that's just 0. And if at the end of the day, this whole volume will be equal to 1/5 times pi. So some of the things I want to point out in this problem was, hopefully this was more straightforward because I just told you the function that we're going to revolve. I told you the lower bound, upper bound, as well as we revolved around the x-axis. Some of the things we're going to cover in classes, what happens if we revolve around a different axis? So instead of the x-axis, what if we revolve around the y-axis? What if we revolve around a horizontal line like y equals -7, or a vertical line like x equals -2, or x equals +4? We're also going to think about what happens when we want to compute the volume between two shapes. So this would be like we have a smaller shape inside of a larger shape. Spoiler, we just subtract the smaller shape from the larger shape, but we'll get into all of these details in class. See you soon.